So thank you very much again, and thank you to those of you who came this morning. So let's just recall some things from the last lecture first. Right, so I have, last time I discussed finite dimensional open systems, time independent. Today I will be moving to thermodynamically large systems that can be either open, closed, or more in the line with this topic of this conference, driven either periodically or quasi-periodically. It will not matter. I will be having certain assumptions that I will discuss soon. But let's return to this question of weak ETH, which is believed to hold in full generality. So the weak ETH says that if you start in an initial state and you look at the dynamics of some observable, yeah, time integrate, then your observable should be described by a canonical ensemble of this form. Here is your Hamiltonian. I'm now specializing to closed systems, but what I will discuss can be easily generalized. And these things, which are like conservation laws, so they commute with your Hamiltonian. I have discussed before, in actual full generality for all types of Hamiltonians, observables, and initial states, this cannot be true, because you can always cook up a weird Hamiltonian or a state or something that violates this, okay? And it's intimately tied to the following question, this issue. What kind of QA should we put here, okay? So is this enough? Is enough that Q alpha commutes with the Hamiltonian? Can I put, for instance, Q alpha to be a projector to an eigenstate of my Hamiltonian? Is this okay? So I will now answer this question. So under the following assumptions, I will take locally interacting lattice models in d dimensions. Note the following discussion has nothing to do with integrability. I said maybe closed, driven, open, doesn't matter. Each individual, so pictorially it is represented by my beautiful drawing here. Each site has a finite dimensional Hilbert space, so no bosons, yeah. This initial state, I assume to have clustering, as I mentioned before, so just a reminder, which means that if these local observables are far enough from each other, then the correlation just decouples into this disconnected part. And by local, I mean the observable acts only on some finite region of the system, yeah? That's my local observable that I index with X. Okay. Now, I will follow Doyon communications in MathPhys, but I will give you so 217. So we need a framework, right, to treat these types of problems, and this is one very powerful framework. So what I will be discussing now, you will not find in the paper. The paper is very technical. I will give you an intuitive explanation. Moreover, I will do even better than that. I will, well, maybe better or worse, I don't know, but what I will try to do is, we'll try to figure out this together, yeah? So what kind of QA alphas I need to put in here? Okay, so what do we want? Let us help ourselves. This can be further generalized. Now, this is an important point. I will assume that we are in what kind of equilibrium state are we in? Well, let's say we are far away from a phase transition. We are at high enough temperature, yeah? This can be generalized to cases when we are not, right? But let's help ourselves and assume that we are at high enough temperature that there is no phase transition, okay? So by definition, and let us help ourselves again by, without loss of generality, assuming that the state is actually just this, yeah? Okay. And okay, so we are far away from phase transition. By definition, this thing, the expectation value of local observable, and now let's say for sake of simplicity, I will just drop most indices, and my expectation value with respect to a state mu will just be denoted like this, yeah, okay? This must be an analytic function in mu. Okay, so what does that mean? Well, that means that the derivative of this thing must exist. And now, since I'm doing a standard Blackboard talk, I believe I have the privilege to set problems. Okay, so problem number one. But before I get to the problem, let us assume, without loss of generality, that this holds. Expectation value of Q, mu in the state is 0. If this is not true, because I have a normalization actually here, if this is not true, if this is non-zero, I can just reabsorb the expectation. I can just take minus here of that and reabsorb it back into the normalization. So I can assume this, yeah? Yeah, now, this is a technical point, but it's useful to assume it like that. Okay, so like I said, yeah, this must exist. And now, yeah. Okay. Okay, so now if you take the derivative, what you see is that since it's analytic, what must hold is mu. Let's not be nice here. So now, indeed, in the thermodynamic limit, so V is the volume of the system, this must exist. And I ask you as a problem to find this. Yeah? So just take the derivative, use this condition, and then you say this must exist for all mu, even in the thermodynamic limit. So this is my first condition on Q. Q must be such that this exists, okay? Moreover, it must exist, and if this must be non-zero, at least for some local observable O. Because if this is 0 for all local observables O, then Q does not contribute to the anything that you measure, yeah. So this must be non-zero. It must exist for all observables by analyticity, and it must be non-zero, otherwise Q is trivial, yeah. Okay, right. So yeah, like I say, it's very simple. You just assume this, yeah, and then you take the derivative. This is the trace, of course, yeah. Okay, so that's one property we need. The second property we need. Okay, what else do we want Q to be like? Yeah. Well, let's see. So, QO mu. Now, let us help ourselves a bit again with an additional assumption that may be actually relaxed. Let us assume that there is some notion of translational invariance in the system. It doesn't have to be an actual translation invariance, just that there is some sort of a map that if you shift the system, there is a well-defined transformation how you do it, yeah? So for instance, if I move everything like this, it either gets some phase or it stays the same, yeah? Right, so let me now write this out. Okay, so this, since I can do this, I can compute the expectation value of Q. Now I want to be careful here because, so now I restored the index X, but I have assumed translation invariance, so I'm free to take the sum over X here and divide by the volume. Okay? Mu. Now, exercise number 2, see our state, it's of this form. It has no 0 eigenvalues. That means that expectation value for any such thing of mu is greater or equal to 0. Okay, so it's kind of like an inner product, if you will. So this is okay. And what does that mean? Well, that means in this expression we can invoke. Sorry, was that a question? Okay, we can invoke Cauchy-Schwarz. So Cauchy-Schwarz. And right, so that means that Q dagger Q mu divided by the volume times 1 over the volume sum over xy, station value, not A, OX dagger, OY. Yeah. So that means this, yeah. And of course, like I said, we want this to exist in the thermodynamic limit as well. Therefore, we recall our clustering condition, okay? And we recall the following. We recall that Q is such that since Q of T, yeah, O, 0 equals Q 0 of mu. Because Q, by our assumption, commutes with the Hamiltonian. So, since I got the mu here, sorry, and I need to put this here. Okay, so by clustering, yeah, since this is equal, we can invoke clustering on the mu as well, yeah. And this will separate, so this will actually not scale as the volume squared, it will scale as the volume. Therefore, for this to exist, it must be bounded, yeah, by this thing. We want it to be bounded. So since this volume, that cancels, yeah. And we, in other words, this Q dagger, Q mu, must scale as the volume. Okay. Now we have two conditions on what kind of Q we need to put in. And now it turns out, Leon shows, and I will not show this, we have these two necessary conditions, let's say. It turns out that they're also sufficient. In other words, these are the only conditions we need for this thing to be well defined. Okay. So what I wrote here is not very rigorous, okay, as you may see, and it's the assumptions are kind of seem restrictive, but they can be very much generalized. For instance, to cases where we have several Qs that do not commute. In that case, you will not use a state of this form. You need to use a state that has a path ordered, some sort of path ordering, yeah. Or, like I said before, if there is no, if there is some sort of a non-analyticity, there are ways to generalize this. But then you have to do things like GNS constructions and so on, which are perhaps too technical. And anyway, in this framework, we will be able to treat the main motivation for our talk here. As you remember, the motivation is non-stationarity. And one very topical example of non-stationarity are quantum many-body scars. So, and with this framework, we will be able to treat quantum many-body scars. Moreover, we will be able to solve for dynamics, not just at zero frequency. So first, this is true, yeah, under these assumptions. That's first thing, yeah, that's true. The weak ETH is correct. Secondly, what about strong ETH? Well, no. So you can fix it, provided that you put here e to the I omega t, yeah? So put here e to the I omega t, and then here you need to generalize this to what I call a time-dependent Gibbs state. Not generalized Gibbs ensemble, because it is, but I don't want to confuse. This has nothing to do with integrability. So e to the I omega t q alpha, where now q alpha for a closed system satisfies, well, okay, we can have several alphas. Have several alphas here. Yeah, I also need the integral now from 0 to t. So I need to do like a Fourier transformation of my state as well. 1 over t dt. What else do I need? Yeah, I think I'm okay here. Yeah, okay. So this generalizes to this dynamical symmetry condition where Q alpha satisfy these two conditions that I will discuss in a second. So that will be the rest of the talk. And then moreover, since this is true, I mean provable, you can use it to solve for dynamics at 0 and finite frequencies. Yeah, exact solutions. Okay, so note that here so far I have not discussed anything about the dynamics. So I would like to discuss a bit about the dynamics. I've just discussed properties of this state. Okay, but let's first see intuitively what these two conditions mean. So these conditions define an operator, or more precisely a quantity, because it's like in the thermodynamic limit, that we call pseudo-local. You may have heard of related concepts such as quasi-local. Pseudo-local is a generalization of local and quasi-local. So what's an example of a pseudo-local quantity? Well, the simplest example is just local, what people call local, kind of overloading the term, but okay. So what is local? Let's say we have our infinite dimensional thing. It lives like this. It's, yeah, it lives like this. And let's say that our Q is a sum over all the sites of some little q that lives on X. So like little q lives here. This is Q1, this is Q2, Q3, and so on, yeah? Okay, so for instance, this is total charge in your lattice, yeah? Total spin in the Z direction. That's local and pseudo-local. And the exercise prove that this is pseudo-local as far as these two conditions for any initial state, for any state that has clustering, yeah? What's not pseudo-local? Well, let's say we take this same system and we define, I'm gonna have projector to an eigenstate of my system. Yeah, Q. No Q, not Q, it's something. It's not a Q, it's not pseudo-local. And exercise, take, say, infinite temperature and check whether you can, let's say, take a Hamiltonian, blah, blah, numerically see how, whether or not these conditions are satisfied, okay? Right, so that's kind of pseudo-local, yeah? Right, so now what about the dynamics? Well, I'm again gonna specialize. I'm not gonna consider states that have clustering in full generality, though this can be made very, very general. I will consider initial states that are of the form, that are of this, well, this form, but are out of equilibrium. So the initial Q's do not commute with your Hamiltonian, or they are not invariant under the, you know, time evolution of your periodically driven system or open system or whatever. Rather they're whatever you like, yeah. So you pick some initial state. For instance, you say you do a quench, yeah, you take a thermostate and then you change the Hamiltonian. That's an example. Okay, so exercise. Take Q to be actually local, and take, say, your Hamiltonian to be some two-side thing, yeah, in 1D. And then check that under the action of the Hamiltonian, this state, the Q that's on top, Q of T, remains pseudo-local. Yeah? And these types of states that have e to the something pseudo-local are known as pseudo-local states. This is by Doyon. Okay, now let's move to calculating the dynamics. And here I give you my recent work. I'll give you the exact references for everything. I'm just sketching them now because, yeah. Okay. Right. So now, yes. So the motivation for my talk. So what can I erase here? I want to keep these two conditions. Okay. Let's maybe. Okay. I guess you can probably remember the setup already. The assumptions. So let's erase the assumptions. Okay, so the motivation comes from something known as quantum many-body scars. So, well, a couple of years back, well, I don't know how many years back, 5, 6 years back, there was an experiment in Rydberg gas, with Rydberg atoms, and they saw persistent oscillations, even though they expected by strong ETH to see thermalization. Later on, a group in Leeds and collaborators, Papic and Banin and others, they had a theory paper that showed that this model, so it's known as the PXP model, had something called quantum many-body scars, which are eigenstates of the Hamiltonian that have low entanglement. I prefer not to work with eigenstates because in the thermodynamic limit you have to be very careful. I'll work with things that are easier to control. But anyway, the physics, right? The physics will be the same. The physics is they find that for certain initial states, for a certain one initial state actually, you see persistent oscillations. For generic initial states, you see thermalization. And hence, if you know single body scars, that's the analogy. Yeah? Okay, right. Are there any questions at this point? The odds of what? Of finding such a state which will show such stars would be very, very small. Yes, yes, yes. So, it's interesting they found it in well, it's then in a sense these states are natural for the system. You'll see what I mean in a minute. Okay, so how can we understand scars? Well, some in okay, let me just first perhaps in total silence rewrite my conditions for pseudolocal. Well, the Young's condition that I use. So now I'll use the conditions. Pseudo-local, number one, exists limit e goes to infinity, station value of O Q with respect to my state. That now, as I said, this can be generalized. You can have more of these inside. So let me just put expectation. So let me just put expectation value here. Yeah. Number two for a general state. Number two. Okay. Q dagger Q scales as the volume. Okay. So this is pseudo-local. All right. Okay, so now these scars have been understood in terms of something that people call is a misnomer restricted spectrum generating algebra. A spectrum generating algebra means this, but it's as you will see soon, you require more than spectrum generating algebra. Pseudo locality will be crucial. Yeah, that's the crucial thing. It's so hence I call it a dynamical symmetry, because the difference between a spectrum generating algebra and a dynamical symmetry is the same as the difference between a projector to an eigenstate and the actual conservation law. That's physically relevant, yeah, for your ergodicity breaking, yeah. Anyway, so let's say, let me now write some condition. Without loss of general, okay. Here, okay, so restricted spectrum generating algebra. Okay, so this is the definition, okay? And now under, if you have certain other conditions, you can show that A, using this relation, A acting K times psi 0, which is some eigenstate of your Hamiltonian, usually the ground state. I believe there was a talk last week by Hosho Katsura about this. I was not here, so but I assumed he discussed this, so I will not go into too much detail here. But anyway, yeah. Yeah. Sorry, I forgot the Hamiltonian. Oh, embarrassing. Okay, psi 0. Okay, so A to the K acting on psi 0 generates more eigenstates of the Hamiltonian that are equally spaced in energy by omega. Okay. So reference for this, there are standard references, but I will show them later. But let me just briefly remark. In 2018, a couple of years back, before people started looking into this, I gave these conditions in the supplementary of my paper, generalized for Lindblad. But no one seems to cite that. So, but let me now still give you. I'll give you all the references. Natcoms, it was published, yeah, then it was published in 2019. Anyway, it's in the supplementary, generalized for Lindblad. Okay, so what's about this thing? So what is this thing? Is it related to what I just discussed? Well, it turns out, yes, it's very much related, indeed. So this is the motivation. I want to understand scars, but let me give you first a general recipe for solving dynamics at zero and finite frequency. Once again, nothing to do with integrability. And in fact, integrable models are the ones that are the most difficult to treat in this approach. Yeah. So yeah. Okay, let's know. So yeah, archive 2301. Okay, so what is the recipe? Okay, so first, let me define a few things. Sorry, my iPad is a bit crazy. I don't want to forget. So, okay, pick whatever locally interacting model you like, open, closed, driven, whatever, yeah? And you want to solve dynamics. Okay, so I want to solve for I want to find my expectation values of observables at any frequency, yeah? Okay, and then you pick any initial state you like that has cluster. Okay, yeah, so you pick, okay, so you pick, what did I say, you pick your model, let's say closed H or more generally some tau T, okay? And you pick some initial state that I'm going to now call row 0 that has clustering. So in general, it can be row 0. So now let's say you are kind of you are clever. You found some structure, yeah, that has this property. You find some operator that has this property. For closed systems, let's say omega A, yeah. Omega can be 0 as well, then it's a conservation law. You found this, you found a set of these, yeah. So let's put set here. So I'm gonna index them with alpha again, yeah. Found a set of these. And now you say, okay, are these operators pseudo-local? Because if they are pseudo-local, I claim that you just, okay, here, okay, let me, if they are pseudo-local, I claim that the solution for your problem is just putting them in here. So here I forgot T, sorry, here I forgot T to the I omega T. Putting them in here. Okay, you put them in here, that's your solution. These chemical potentials will be fixed by your initial state, okay? So if they are pseudo-local, they go up in the exponent and you're done. If you find all of them, yeah? You kind of have to, that's the trick, you have to assume you know all of them, yeah? And if you're in a chaotic model, it's easy. So there's no such thing. There's only the Hamiltonian, yeah? And then your solution is just the thing that weak ETH says that may be evaluated using various tricks. Okay, if you have an integrable model, you have an infinite set of these at 0 frequency. Note oscillation, persistent non-stationarity, persistent oscillations have nothing to do with integrability, quantum integrability. Then you have to have an infinite set of chemical potentials that you have to evaluate, and this thing may not even converge, then you are in trouble. And yeah, but non-integrable are easier to solve in this sense. Okay, right, so let's do that. So let's discuss this. So the solution is guaranteed to be correct, yeah. Okay. Okay, so first we need to check whether or not this is pseudo-local. So how do we do that? Well, we have picked our initial state. Okay, let me write. So for periodically driven systems, this is the, or I mean any driven system, this is the condition you need to check. And I believe that, yes, open, close, whatever, and like in Subjahid's talk, this also applies to time crystals. Okay, yeah, so this is the condition. These two, you identify some set of these, right? And now you're asking yourself, okay, are these pseudo-local? Because if they are, they have to go up there to give you the correct solution. So how to check this? Well, it turns out it's possible to check. So, and the trick to check is the following. The trick for first thing you need to do is you need to compute, you need to see whether or not condition 1 holds, right? So, okay, condition 1, but let's, where did I, condition 1. Okay, condition 1 or condition 2. Now, if you think about it a bit, let's say I find some Q that grows as, so I check condition 2. I find some Q that grows as exp of V. Yeah, so it grows exponentially with the volume. Yeah, this needs to be done with respect to the initial state. So 0, yeah, T equals 0, yeah. So with respect to the initial state, it grows exponentially. But then you say, okay, well, but I don't care. So what? I just divide Q, I redefine Q to be divided by exp of V times V, yeah. If you do that, then it will turn out that this condition will be true, but it will be trivial if generically, it will be trivial in the sense that this will always give you 0 for all local observers. So such a Q is indeed pseudo-local because you have forced it to be pseudo-local by dividing by exp of V times V, but it doesn't contribute to anything. Yeah? So you need really, so the first way to check whether Q is pseudo-local, or A, sorry, now A. I don't know why I switched this notation, but okay. I wanted Q because it's more generally, you know, the letter used for conservation law. But now I have wanted to emphasize it's no longer a conservation law, it's a dynamical symmetry. Anyway, so first condition, you say, okay, QO is 1 for some local observable O. You can do this without loss of generality. You can always rescale the Q, and if you rescale the Q, it goes into the Z. So you can, if Q is provided it's finite, yeah. Okay, and then what local observable will you pick? Well, usually it's easiest to pick something related to the Q you found, yeah. Okay, let's say, so if it's quasi-local, if it looks quasi-local, then you pick some local density inside, and then you fix it to be 1, yeah. With this condition, so this kind of, okay, let me call this Q tilde, or sorry about this, A alpha tilde, yeah. And now my A alpha will actually be this renormalized thing that I fixed by fixing this condition. So I fixed this renormalization. Okay, and now I need to check whether or not this grows as V. Yeah. And if this is true, then it's pseudo-local. Then you can put it in the time-dependent Gibbs state and use it to find solution for the dynamics of all local observables. Yeah. Okay, now clearly you also need to fix the state completely. So you fix it by fixing the chemical potentials, because you have identified your A. Yeah. You have identified the frequencies of A at omega alpha. Now the only thing left is to, the only unknown is the chemical potentials. And these are fixed by the initial state. And these are fixed by the initial state by the following simple condition. A of 0 equals A of t equals 0. So when I put 0 in this state, then I'm going to explicitly write, which I call the t time-dependent Gibbs ensemble, which is e to the minus theta mu plus sum over alpha mu alpha e to the I omega alpha t A alpha divided by z of t. Yeah. Okay, at t equals 0. Okay, so and you solve for this, then you fix this fixes these. Yeah. Okay, like you do in Gibbs, like you do this for standard Gibbs. Yeah. Also, I explicitly took out beta h to you know, remind you of a Gibbs state. H is like a special case of this when omega is 0, right? But I took it out, so it has a beta. You need to fix everything. Yeah, all the temperatures, the chemical potentials, whatever. Okay, that's it. Now, once you have done that, you have this formal solution. You need to evaluate, of course. And now we will see how to do it, and we will see how to do it for scars, as an example. This works for all models under these assumptions. Okay. Okay, so what about scars? So scars indeed, interestingly enough, have pseudo-local charges that I call projected local. I call them projected local. Why? Well, notice crucially, very important property that I would like to really emphasize. Locality, pseudo-locality is always defined with respect to a state. It's not a property of just the operator, it's also a property of the state. And scars do have pseudo-local dynamical symmetries. that are what I call projected local, and you'll see in a second. Note that this restricted the spectrum generating algebra. Now here's the crucial thing. If A itself is pseudo-local, or actually simply usually just local, then let's say I define, okay, let me call this psi of k, this set of eigenstates, and now I define a projector to these eigenstates. There's a projector. And now my actual thing that may be pseudo-local will be A, P, A. So this A. So when is this thing pseudo-local? Well, you say it cannot, this is no way this is local in any sense that I know, right? Because I have a weird projector here that's doing everything. But if there are certain initial states for which trace rho 0, P, A, P, yeah, or more specifically, rho 0, P equals P rho 0, which equals rho 0. Initial states that are contained fully within this P, yeah, essentially, yeah. And for these, when exercise, use that and show that if A is pseudo-local, PAP is also pseudo-local for such initial states. So indeed, it's projected local. That's why I call it projected local. It's type of pseudo-local. It's projected local. Okay. Let's see. Okay, now you say, well, okay, that's all well and good. So I have my, but this is difficult to evaluate, right? I know that even e to the beta h is difficult to evaluate. Expectation values I need to do, I don't know, some fancy numerics or high temperature expansion, low temperature expansion. You can do all the tricks there, here as well, out of equilibrium for the mu's and the betas. All of these tricks that you know from equilibrium you can use. However, if you want to be very, well, not sneaky, but cheat, I don't know what's the right word, you can use tricks. So for instance, if you find that your A's are kind of simple, and then you want to evaluate only for certain initial states that have certain symmetry properties, let's say discrete symmetry properties, they say, oh, my Hamiltonian is many body, this is difficult to evaluate. But yeah, let's say I pick an initial state such that P, no, not the same P, some other P, R rho 0 R is minus rho 0 or plus minus rho 0, and R for some discrete symmetry. This is a trick you can use. Is minus plus H, yeah? Minus plus, yeah? So the opposite, it has the opposite parity, let's say, yeah, from the initial state, the Hamiltonian. Then this beta is 0, so you're just left with this thing, which can be simple. And indeed, this is what we will use to do exact solutions in one prototypical example of scars. And now I would kindly ask for the screen to be lowered. Huh? Okay, so this is what we discussed yesterday. Okay, so this is a model of quantum many-body scar. It's not the PXP. It's another model that's more instructive. What I want to do is due to Schroeter and Edekola, who's over there. It is a spin-1 model of interacting spin-1 model. You have like two fields and so on. So as shown in this PRL, there is a spectrum generating algebra of this type. I now need my thingy. Okay, so there is a spectrum generating algebra of this type. This is just the thing I showed here, and these are these eigenstates that you make by. So this is like an SU2 algebra. This J plus J minus, know that there is like, it's at moment, all of these spin raising operators on the site X squared. Yeah, it's spin 1, okay, at momentum pi. And this is like an SU2, and you can show that the relations hold, and then you generate these, okay, here they call them n psi of k, yeah. And okay, and indeed, now you can construct something that's possibly a projected local dynamical symmetry. You have this projector to this set. I define these things, like I said in my construction. So this is like some volume normalization that I need to find, yeah. And it's easy to show that this holds where lambda is 2 of h, yeah, so this h, yeah. So we need to find f of v in such a way, if we can, that a plus minus are pseudolocal. Okay. So in the paper, because of this, because of this very nice representation theory, they could treat, Tom and collaborator could treat one initial state. Here I will show you generic initial state. In fact, let's say this initial state. So I want to study dynamics at 0 at finite frequency from this initial state. So it's like, I don't know, Jx in some direction, yeah. And provided that these A, so now I need to check whether A plus minus are pseudo-local with respect to this state, okay? And if they are, then this is the solution. Okay, so like I said, we kind of, yeah, we need to renormalize, so it's 0. Yeah, oh, I forgot to say that. We need to remember that's one of the initial things we did. So we kind of take A minus so that it's traced with respect, its expectation value in the initial state is 0. Then let's assume that this is, yeah, what I just said. And without loss of generality, I said before, yeah, we can pick as the observable to normalize to 1, just the density of this thing, yeah. So J minus on site X, for instance, that's 1. It's easy to show that, it's easy to fix the chemical potentials because this thing has an opposite parity from the Hamiltonian, apart from this term, yeah, which is just a single site, so it's easy to fix everything analytically. In particular, mu equals mu 0. Okay. Right, so now we need to check. And indeed, it turns out that these things are not pseudo-local for generic mu 0. For mu 0 infinite, they are, and indeed this corresponds exactly to the solution found here. For finite mu 0, they are not. In fact, they grow exponentially. So they don't grow with the volume, they grow exponentially. However, something very interesting happens, and this is like a thing that this is now an interesting thing. I find this kind of quite unusual. They can grow for certain finite values of mu, large, relatively large, but finite values of mu. They can grow extremely slowly with the system size. So you can see here. So let's say system size 200, 400 up to 1,000. They practically don't grow at all. Yeah. For this value of mu. Okay, so what does this mean? Well, that means, and I forgot to mention, there is something called a Lieb-Robinson bound in these local interacting systems. Okay, so let's say I want to know dynamics of local observable. Here, the local observable is here. I have a really, really big system, and my local observable is somewhere in the middle. Let's say the system is big, but still finite. So how will the dynamics look? Well, let's say I start in a relatively translational invariant initial state, let's say here at momentum pi. By certain arguments, you can, well, argue, not prove, but argue that the observable will be described by the state asymptotically reach very quickly. So it will take not too long time to reach the asymptotic state. And it will not take too long time to reach the asymptotic state, whatever it is. In our case, if A were really pseudo-local, it would be this state, the TGG, yeah, the TG. Now, okay, so that's okay. So now, finite but large systems, when will the system see it's not really infinite? Well, it will take some time for a signal to travel back once I'm evolving my observable, travel to the end and back. And this takes times order of system size by Lieb-Robinson bound, okay? So up to these times, effectively, my state describing the system is this, with these things inside that are not pseudo-local really, but they are effectively pseudo-local for finite systems. And it turns out, this has physical consequences. Let's say you don't know how to do this theory that I have just discussed, and you want to do numerics or you want to check this, and now you pick some system size. You can do very good numerics, so you pick system size 100. So a really big system, or 150, even better. And then you pick some chemical potential for the initial state. This is, by the way, the solution to the dynamics of Jx. So it's an example of an observable, Jx at site x. So x in the x direction. And here I mean just this frequency, finite frequency. So this is the amplitude at frequency 2h. Yeah? And what you will find is, oh, it's 1. So great, and you wait long enough, you wait like times t equals 100, and you don't believe after that, you know, it's going to show finite size effect, so t100 is okay. And you see, okay, the amplitude is 1, I have persistent oscillations, I have scars, yeah. But now you say, okay, and then you say, okay, now I'm going to do numerics for 151. Boof. The amplitude is 0. There is no oscillation. And I call this a scarring phase transition, yeah? So it's really effectively the reason for this, it's a different kind of phase. It's not an equilibrium. It's nothing to do with any, if you ask me about universality classes, I have no idea. It's a completely different kind of phase transition. It has nothing to do with anything that I can understand with normal equilibrium phase transitions. It's simply due to the fact that an operator stops being pseudo-local. Okay. Likewise, okay, you can also do zero frequency here. I give an example. So I can fix the beta for small, let's say mu0, that's the easiest thing to do. They fix the temperature, and then you kind of can just, you know, this is a zero frequency. So I pick this YY correlator, nearest neighbor, and here are the results for various values of H and D. Yeah? Analytical, yeah. So, okay. So one thing, how much? 1 minute. Great. So one thing you may ask, okay, you have solved the finite frequency dynamics, which is good. But what now you have just told us that finite time dynamics can be also interesting, and yeah. So, but indeed, you can also do the same thing for finite time dynamics. But now you have to have these lambda k's. You can show, you can prove that they can acquire real parts. So here minus or negative real part. So you can actually have pseudo-local quantities. I no longer, can you call, pseudo-local dynamical symmetries, but decaying ones, yeah, that exponentially decay as well. There are no known examples. I just proved that they must exist. So this is how a quantum system thermalizes. Quantum locally interacting system thermalizes. You start in an initial state that has clustering. Immediately you can rewrite it in this form, with these being pseudo-local. And then the ones that have real part will decay, and you will be left over generically with just the Hamiltonian. If this is for ergodic system, it'll just be the Hamiltonian. And this is the picture of that. Okay, this is now just a PXP model, right? So you can see here there is a special initial state where they see persistent oscillations. And yes, so here are the references for today's talk. Yeah, DTH, all the things about scars. I'm good. spectrum restricted, quote unquote, spectrum generating algebra. Doyon, remember, if you like C-star algebra, okay, and this main thing I talked about. So okay, that's it. I'm open to. Thank you for your attention. I'm open to questions.
Thank you, Berislav, and thanks. Yeah, any questions for Berislav?
The phase transition you mentioned, is this just in the scarred eigenstates? The rest of the spectrum?
No, there's no. It's not in any. There's no eigenstate here. I'm doing. Doing this. There's no eigenstate. There's an initial state.
Okay. Forget about that. I mean, my question is more like it's not there's a sub-extensive number of states that are scarred. So I'm just wondering,
So the number of scarred states is indeed extensive. However, what I would like here to convince you is that forget about eigenstates. Eigenstates are anyway thermodynamically difficult to treat. Yeah, one should think in terms of physics, right? So physics is local, at least in local interacting systems, and one should focus on what observables do. Yeah. So to answer your question, yes. So there is an extensive number of eigenstates that have scarring. Yes.
Okay. Thanks.
Thank you. But that's directly. You can have. I assume you can have scarred models that do not have this. Yeah. Or perhaps do other models. It's an open question. Yeah.
Hi. Hi, I just wanted to understand this slide relating to that question. So suppose you fix your mu naught to some value.
Yes.
Are you saying that there is a specific number of size which you cross, and after that you don't see any persistent oscillation?
That's right.
That's basically what you're saying.
Yes, yes.
Okay, yeah.
And this may have relation to what people discuss. So the PXP, it's kind of open, remains kind of open, whether or not it's truly scarred and whether or not these persistent oscillations survive in the actually for infinite times, actually infinite systems. So I think this is probably related to this question. This is a simpler model. I mean, more instructive, let's say. Yeah.
Okay, if there's no further questions, I'm going to ask one.
Yes.
So I was wondering about the technical assumptions. So clustering seems pretty strong. That kind of includes all states with order, I guess.
Clustering is not very strong. I mean, can you give me a condensed matter state that does not have clustering?
Then maybe I don't understand it, because I thought it means all correlation functions factorize into single
when the observables are infinitely far apart.
Right, but I could have long range order where they are just constant, couldn't I?
Yes, this is the only example. Yes. So, but power law is okay. Finite temperature is okay. Yeah. Gapped ground states in 1D. Okay. All of these. Yeah. Yeah. It's Thank not you. Very. I mean, it's restrictive, but not insanely restrictive. Yeah.
Any further questions? Otherwise, let's thank Berislav again and go for coffee.
Thank you.